To understand water governance in India, we must first deconstruct the legal foundation upon which all regulations stand. You might wonder, curiously, if water is essential for life, why is there confusion over who controls it? The answer lies in our constitutional backdrop. Now, focus. Under the Constitution, water is primarily a state subject, Entry 17. This means states have the power to legislate on water supply, irrigation, and canals. Bilkul, states control it. However, rivers do not respect state boundaries. They flow continuously. Therefore, the regulation of interstate rivers falls under the Union List, Entry 56. Samjhe? This division often creates a conflict of jurisdiction, which is why Article 262 exists, specifically to handle the adjudication of disputes that arise when states fight over river water sharing. But governance is not just about sharing, it is about quality and pollution control. This brings us to the first major legislative intervention, the Water Prevention and Control of Pollution Act, 1974. Before this, there was no structured mechanism to police water quality. This act is the primary legislation that established the institutional machinery we see today. The Central Pollution Control Board, CPCB, at the center, and State Pollution Control Boards, SPCBs, at the state level. Look at the evolution of water law's timeline. It starts here. The intent was clear: prevention and control of pollution to maintain the wholesomeness of water. The key provision here is the requirement of consent. No industry or municipal body can discharge sewage or trade effluent into a stream, well, or sewer without permission. This effectively made polluting without oversight a legal offense. Simple hai, right? However, the 1974 Act had limitations, mainly regarding the broader environment. This gap was filled by the Environment Protection Act, EPA, 1986. As depicted in the timeline, the EPA is an umbrella legislation. Why is it called an umbrella? Socho zara. Because it empowers the center to intervene directly, setting strict effluent standards and superseding other laws if there's a conflict. It introduces the precautionary principle, meaning we must act to prevent harm even before scientific certainty exists. Under the EPA, the government issues notifications for coastal regulation zones, CRZ, and river rejuvenation norms. Finally, how are these laws enforced? As shown in the enforcement mechanism, the National Green Tribunal, NGT, acts as a specialized adjudication body for environmental cases, taking the burden off the regular courts, though appeals and still go to the Supreme Court. Building upon the legal statutes, we must now examine the institutional architecture that executes these laws. We know the laws exist, but who is the watchdog on the ground? This responsibility is split between the Central Pollution Control Board, CPCB, and the State Pollution Control Boards, SPCBs. There is a critical hierarchical logic here that you need to grasp. Listen carefully. The CPCB at the central level is responsible for standard setting. They define the minimal national standards, MNAS. Think of MNAS as the baseline safety net. No state can have standards lower than this. However, can a state be stricter? Yes, bilkul. The SPCBs can mandate tighter norms based on local pollution loads, but they cannot relax the central norms. In the visual depicting institutional roles, you see that CPCB focuses on coordination, technical assistance, and data sharing, while the SPCB is the operational arm, responsible for inspection, effluent sampling, and the actual granting of consents. This consent mechanism is vital for any industry. To set up a factory, you first need consent to establish, CTE, and before you turn on the machines, you need consent to operate, CTO. Without these, the operation is illegal. Look at the distinction regarding groundwater. Many assume the Water Act covers everything, but groundwater is regulated by a separate body, the Central Groundwater Authority, CGWA. As noted in the slide text, the CGWA is constituted under the Environment Protection Act, EPA 1986, not the Water Act. This is a crucial distinction for statutory clarity. The CGWA regulates extraction by issuing NOCs, no objection certificates. Finally, to solve the problem of fragmented governance, where one department handled irrigation and another handled drinking water, the government created the Ministry of Jal Shakti in 2019. By merging the Ministry of Water Resources, MORE, and the Ministry of Drinking Water and Sanitation, MDWS, we now have an integrated water management approach. This integration, shown in the overlapping circles, ensures that surface water, rivers, and groundwater are viewed as a single resource, linking schemes like Namami Gange directly with Jal Jeevan Mission for holistic water security. Clear hai?
Let us transition from institutions to the actual strategies used for cleaning our rivers. Historically, our approach to river conservation was flawed. Why did early plans fail? Socho. The National River Conservation Plan, NRCP, was a town-centric model. It focused on treating pollution in specific cities along the riverbanks, but ignored the river as a continuous system. It treated the symptoms, local pollution, rather than the disease, basin-wide degradation. This lacked a holistic basin approach. If you clean the water at Kanpur but the flow is blocked upstream, the river will still die. Samajh aaya? This realization led to the paradigm shift towards the Namami Gange mission. This is not just a cleanup drive, it is an integrated scientific basin approach. It treats the Ganga and its tributaries as one organic entity. The mission has twin objectives: effective abatement of pollution and absolute conservation and rejuvenation. But how do we define a healthy river? We use two key metrics: Nirmal Dhara, unpolluted flow, and Aviral Dhara, continuous flow. You cannot have a clean river if it does not flow. If water is stagnant, its self-purifying capacity drops. The pillars of Namami Gange visual illustrates the multi-dimensional strategy required. It is not just about sewerage infrastructure, STPs. It includes riverfront development, fixing ghats, river surface cleaning using skimmers for floating trash, biodiversity conservation, protecting dolphins, and public awareness. A river cannot be cleaned by engineers alone. It needs the people. This connects to the concept of Arth Ganga prominently featured in the slide. Arth implies economics or paisa. The Prime Minister's concept acts as a bridge, linking people with the river through economic incentives. If the river provides a livelihood, people will protect it. Correct? This involves promoting zero-budget natural farming, ZBNF, along the river banks. Why 10 kilometers? Because chemical fertilizers from farms run off into the river, destroying water quality. By shifting to organic farming, we reduce chemical load. Additionally, monetization of sludge turns waste into revenue, fertilizer, or energy, and ecotourism generates jobs. This circular economy model ensures that conservation contributes to 3% of the GDP, making sustainability financially viable rather than a burden on the exchequer.
We have discussed the policy, but now we must confront the technological reality of wastewater management. The fundamental problem in urban India is the treatment gap. Look at the bar chart comparing sewage generation versus installed capacity. Sachai ye hai that we generate over 72,000 MLD of sewage, but our capacity to treat it is less than half, and the actual operational capacity is even lower, around 30%. Where does the rest go? It flows untreated into water bodies. This untreated discharge is the primary cause for the drop in dissolved oxygen, DO, and the rise in biochemical oxygen demand, BOD, killing aquatic life. To fix this, we need to understand the STP technologies available. The traditional method is the activated sludge process, ASP. While widely used, it is old, energy-intensive, and requires a large land footprint, which is difficult to find in crowded cities. So, the world is moving towards the sequencing batch reactor, SBR. As noted, SBR is modern and compact because it performs multiple steps, aeration and settlement in a single tank, making it highly efficient at handling load fluctuations. For even higher quality output, we have the membrane bioreactor, MBR, though it is expensive. A critical debate in policy is centralized versus decentralized treatment. The diagram shows the difference. Centralized systems pipe sewage from all houses to one giant plant. This is expensive to build and maintain. For peri-urban or rural areas, this is prone to failure. No, not exactly feasible there. The solution is decentralized wastewater treatment, DWWT. Here, we treat water locally, right where it is generated. Technologies like Jokaso, an on-site packaged treatment system popular in Japan, allow for local treatment. This leads to a reuse loop, where treated water is used for toilet flushing or gardening within the community itself, reducing demand for fresh water. The policy framework supporting this is SRAP, National Framework on Safe Reuse of Treated Water, which actively encourages using this treated water for agriculture and industrial cooling, closing the loop on water usage. Make sense? Industrial pollution is distinct from domestic sewage because of its toxicity. We classify industries that pose the highest risk as grossly polluting industries, GPIs. These include sectors like distilleries, tanneries, and textiles. Why are they dangerous? Socho zara. They discharge heavy metals and toxic chemicals. Historically, monitoring them was physical and periodic. An inspector would visit and corruption was possible. To eliminate this, we now mandate OCEMS, Online Continuous Effluent Monitoring Systems. As the OCEMS architecture diagram shows, sensors are placed directly at the industry's effluent outlet. These sensors transmit real-time data on parameters like pH and BOD directly to the CCPB or SCPB servers. If the limits are breached, an SMS alert is triggered immediately, ensuring constant surveillance without human interference. However, the ultimate goal for industrial pollution is not just monitoring, but eliminating discharge entirely. This is the concept of zero liquid discharge, ZLD. Look at the ZLD cycle diagram. It represents a closed-loop system. In a ZLD plant, no liquid waste leaves the factory premises. How is this achieved? The wastewater goes through pre-treatment and then into a reverse osmosis RO plant. The clean water from the RO is recycled back into the factory process. The reject water, highly concentrated waste, goes to a multi-effect evaporator which boils it off, leaving behind solid salts. While ZLD is the gold standard for river protection, it comes with challenges. It has a very high energy cost and produces hazardous solid waste salt that must be disposed of in landfills. Because ZLD and high-tech ETPs are expensive, small industries, MSMEs like the tanneries in Kanpur cannot afford them individually. For them, the solution is Common Effluent Treatment Plants, CETPs. This is a shared cost model where multiple small factories send their waste to one common facility for treatment. This makes pollution control economically feasible for the MSME sector, while ensuring ZLD mandates are met in critical river basins. Got it? Groundwater governance presents a unique challenge because the resource is invisible and over-extracted. You cannot see it disappearing until it is gone. The current regulatory regime relies on the Central Groundwater Authority CGWA guidelines. The primary instrument of control here is the No Objection Certificate, NOC. It is mandatory for new and existing industries or mining projects to obtain this NOC to extract water. However, notice the exemptions. Individual households and the agricultural sector are largely exempt. Listen, since agriculture consumes nearly 90% of groundwater, this is a significant regulatory gap. To manage industrial extraction, the government levies a Water Conservation Fee, WCF. Look at the Water Conservation Fee structure matrix. The logic is based on scarcity. Areas are categorized from safe to overexploited. If an industry extracts water in an overexploited zone, red, the fee is significantly higher than in a safe zone, green. This financial disincentive is designed to discourage water-intensive industries from setting up in water-stressed regions. Simple economics, right? However, regulation alone cannot save groundwater. We need demand management. This is where the Atal Bhujal Yojana, Atal Jal, comes in. It is a central sector scheme focused on community-led sustainable groundwater management. Why community-led? Because you cannot police millions of farmers from Delhi. Now, possible. The approach is strictly participatory, as shown in the flow on the right. It begins with data by community, or water budgeting. Villagers calculate how much water it receives from rainfall versus how much they use. Based on this, the Gram Panchayat creates a water security plan. This encourages demand-side measures, like switching to drip irrigation or sprinklers to reduce usage. The scheme targets water-stressed areas in 7 states, like Gujarat, Haryana, Rajasthan, and uses a cash incentive model where funds are released to states only upon achieving performance benchmarks, ensuring accountability and actual results on the ground. To manage water effectively, we must accurately measure its quality. This involves a robust water quality monitoring and assessment framework. In India, this is executed through the National Water Quality Monitoring Program, NWMP. This network is a collaboration between the central CPCB and state SPCBs. It operates through 2 main systems, GEMS, Global Environmental Monitoring System, and MINERS, Monitoring of Indian National Aquatic Resources. As the diagram indicates, samples are collected monthly or quarterly from fixed stations to track changes over time. But who has the legal authority to act on this data? The Water Quality Assessment Authority, WQAA, constituted under the Environment Protection Act 1986. It has the power to issue directions for water quality management. However, chemical analysis, checking pH or BOD, has a flaw. It only tells you the quality of water at the specific moment the sample was taken, just a snapshot. If a factory discharged poison an hour ago and it washed away, chemical tests might miss it. This is why we need biomonitoring. Biomonitoring uses indicator species, specifically benthic macroinvertebrates, small insects or organisms living at the river bottom. These creatures are sensitive to pollution. If they are present, the river health is good over the long term. If they are absent, the river is stressed. It complements chemical analysis. Based on these parameters, the CPCB has created the Designated Best Use classification. Look at the pyramid. It classifies water from Class A to Class E based on what you can safely do with it. Class A is the highest quality, drinkable with disinfection. As you go down to Class B, you can bathe but not drink. Class C is potable only after conventional treatment. Class D is suitable for wildlife propagation. Fish needs minimum oxygen. Finally, Class E is only fit for irrigation or industrial cooling. This hierarchy helps policymakers target specific river stretches for specific usage upgrades. Very logical, right?
Finally, let us look at innovative solutions that leverage nature itself to repair environmental damage and the ecological risks associated with poorly planned infrastructure. Nature has its own cleaning mechanisms. Bioremediation is the use of microorganisms, bacteria, to degrade pollutants. A prime example is Oilzapper or Oilivorous S developed by Terry. When an oil spill occurs, these bacteria are applied to the sludge. As shown in the Oilzapper mechanism visual, the bacteria eat the hydrocarbon chains in the crude oil, breaking them down into harmless CO2 and water. Amazing, isn't it? Similarly, biotoilets developed by DRDO use anaerobic bacteria to convert human waste into water and gas, solving sanitation issues in extreme climates. Another nature-based solution is phytoremediation, using plants to clean water. Certain plants like water hyacinth or cannas have root systems that absorb heavy metals and nutrients. We engineer this into constructed wetlands. Look at the cross-section diagram. It acts as a natural filter. Sewage flows through a bed of gravel and aquatic plants. The roots and the gravel trap impurities and filter the water without using electricity or chemicals. This is a low-cost, high-efficiency solution for rural areas. However, we must be cautious of riverfront development risks. Modern development often involves channelization, building concrete embankments or ghats along the river. While this looks organized, it destroys the riparian zone or the ecotone, the transition zone between land and water. Concrete embankments cut the river off from its floodplain. Why is this bad? Floodplain encroachment reduces the natural recharge of groundwater and removes the area that naturally absorbs floodwaters. This leads to higher flood intensity downstream. Dangerous hai ye. Therefore, the sustainable solution is not concrete ghats but nature-based riverfronts or biodiversity parks that maintain the natural slope and vegetation, preserving the river's ecological integrity while allowing human access. Bilkul clear.